So temperature is the?
Average kinetic energy.
Yeah, it's the average kinetic energy. Now, do you remember how kinetic energy is calculated?
Yeah.
How do you calculate kinetic energy?
Half mv squared.
Right. Now, it's not physics, so we don't really need to care too much about that formula, but the key important thing I want you to understand from that is, what do you notice about kinetic energy if it's half times m times v squared?
What do you mean?
Can it ever be negative?
No.
Right. So it's greater than or equal to 0, yes?
Yeah.
And as a result, temperature must also be so-called greater than or equal to 0. In other words, you can't get a kinetic energy lower than 0. Like, it's just not possible by our definition. So therefore, you must have a lowest possible kinetic energy, which is 0. And by extension, you must have a lowest possible temperature, right?
Yeah.
What is that temperature?
Absolute 0.
And what is that temperature? Like, so correct, but what is that temperature? I guess, roughly.
Negative 273 degrees Celsius.
Right. Otherwise known as 0 Kelvin, which is absolute 0, which is, when you have no kinetic energy, essentially. That's what we're saying. And that's why you have an absolute 0. Now, because temperature is the average kinetic energy of the particles, why do we need the word average?
Because the particles are moving at different pace.
Yeah, essentially we've got more than one particle, lots of particles. And importantly, they don't all have the same energy. In fact, they definitely don't. Like, there's plenty that have different energies. And since we want one number to describe them all, then we essentially need to provide the average. Now, do you remember how the kinetic energy of the particles are sort of distributed?
Isn't it a curve?
Yeah, what curve?
Boltzmann.
Yep.
Distribution.
So, exactly. So you've got a distribution, which is the Maxwell-Boltzmann distribution. And it looks something like this. And so what goes on the horizontal axis?
Energy level.
Yep. Let's call it KE, given we're talking about kinetic energy, but yes, it's the energy level. And what goes on the vertical axis?
Number of particles.
Right. Of a particular KE. And so you'll see that, you've got quite a few particles that have this particular level of KE. And yes, there's plenty of particles that have more than that, but, as you get more and more and more higher, there's just less and less particles with it. Yeah?
Yeah.
All right. Happy with that?
Mm-hmm.
All right, good. And we didn't really say much more than that last week, right?
No.
Good. All right. Now, I want you to also think about a chemical reaction. How do chemical reactions occur? Or think about the energy of a chemical reaction. How do you get a chemical reaction to happen? So let's say, we've got hydrogen plus oxygen to give us water, for example. For simplicity, let's assume they're all gases. Then how does this reaction happen?
They just react.
All right. So if I put hydrogen and oxygen together, I'll just get water?
No.
Why not? You just told me they just react, right?
Well, yeah.
But I mean, like how, I mean, so, you know, if I put hydrogen and water just together and don't do anything, will I get water?
No. No.
Why not?
I don't know. Because they just don't bond with each other.
Right. They don't actually bond with each other if I just have hydrogen and oxygen. Do you know why?
No.
Oh, okay. So you haven't figured out the why yet. You should probably be able to, by the way. But it's okay. Like that's what kind of why we're going through it. So let me give you another example, right? Let's say wood. Can you burn wood?
Yes.
Right. Which means when you burn it, is it endo or exothermic?
When you burn it, it's
Yeah, when you burn wood.
exothermic.
It's exothermic, right? And that's because it releases energy. Now, wood can burn and release energy. And when you burn wood, for example, what is it reacting?
What is it reacting?
Yeah. What is the reaction?
Combustion.
Right, it's combustion, which means the wood is reacting with,
Oxygen.
right, to get you carbon dioxide and water, right?
Yes.
Yeah, if I just have a wood lying there, normally anyway, would it burn by itself?
No.
Yeah, why not? I mean, it could burn, right? So why isn't it burning?
Because you don't have fire.
Yeah, true. Can you now give a more chemical answer? More chemistry related answer? So you're on the right track, but that's kind of what we're getting at, right? You've got wood, it could burn, but it doesn't. You've got hydrogen and oxygen, it could react to form water, but it doesn't. I mean, not until you know, do something. So why doesn't it? And you should know this. As in, like, you might not have linked it together, and that's what we're trying to do here. But I'm not trying to ask you something you haven't learned before. Well, I don't think so anyway.
Because you don't have heat. Oh.
That's got something to do with it. So I suppose more importantly, or better way to put it, what is that heat meant to do? Or what does that heat sort of, yeah, what does that heat do? Or what does that heat provide?
Energy.
Yes, and why do we need that energy?
To make it react.
What do we call that? I'm kind of missing the...
What do we call that?
All right, so let's draw out your energy diagram or enthalpy diagram. So let's say this is your enthalpy of your reactants. And let's say this is your enthalpy of your products. And given the reactants are higher than the products, this is endo or exothermic?
Exo.
So delta H is positive or negative?
Negative.
Right, which means it's exothermic. All right. Do you know how the enthalpy goes from the reactants to the products?
Do I?
No? You don't? Okay. So maybe you haven't done it then. So right before in chapter 5, you probably just had stuff like this, right?
Yeah.
Okay. So you've never seen it with a sort of like a curve like this?
I think I have.
Yeah, I think we have. So what does this curve mean?
It just means, oh. But what's on the axis? Is it the temperature? Or the enthalpy?
Yeah, good question. So, I mean, like, are you talking about the horizontal or the vertical axis?
Vertical.
Right, so you should know what the vertical axis is. What is the vertical axis?
Temperature.
Not temperature.
Enthalpy.
Think about, yeah, it's enthalpy.
Yeah. I know.
So, what does this curve mean then?
The energy?
Well, I guess it's the enthalpy, which essentially means the energy. But really, we're saying that for the reactants to get to the products, you have to go through this hump in the middle, right? You have to give it more energy than before to start with. And then it can, react and release even more energy. But there's this hump in the middle. It's not straight downhill, right? To go down the hill, you have to go up first.
Yeah.
Right? And so do you know what this is called? The distance that you need to go up. Two words. Second word is energy.
Activation.
Yeah, it's the activation energy. That's why I was like, I'm pretty sure you've done this before.
Yeah, okay.
Yeah. So for a reaction to happen, basically all reactions, they must have you need an activation energy. You need to, almost all reactions, I mean, it will vary, like the size of the activation energy will vary, but pretty much all reactions have an activation energy, which basically means that, well, you're going to need to, put in energy for the reaction to occur. It might be a little bit, it might be a lot, but it's like a, get things going kind of fee, right? You need to do it, get this activation energy happening, and then the reaction can then happen.
Yeah.
All right. Now, that's true, and we kind of should have talked about that before. If we haven't before, we should have. But I'm fairly sure we did. But basically, reactions need the EA to be supplied to be able to proceed. All right. Now, if your reactions need EA to be supplied to be able to proceed, my question is, why do you need an activation energy?
Because you want them to react.
Oh yeah, sure. But I mean, but like, why do you need this fee? You know what I mean? Like, did someone just decide, hey, did someone arbitrarily decide a payment fee? Or like, why, what is this for? Why would we need to supply this energy? Why can't the wood just combust on its own? Why do we need to light it on fire? Any ideas?
No.
No? All right. So you get the idea of what we're thinking about. We're saying that for all reactions, exothermic or endothermic, there is an activation energy that is required. And this is, the EA is equal to the energy required for the reaction to proceed. Yeah? Now, my question is why? And in other words, what is the EA for? Now, let's take a simple example of, for example, hydrogen and oxygen reacting. Now we've got 2H2 plus O2 gas to give you 2H2O, right? Now you know that hydrogen gas is going to be like this, right? Right? And oxygen gas is going to be like this, right? Yeah? And you know that you're going to get sort of this happening. Right? All right. Now, what did you learn in, chapter 5? Like, how do you work out if this is endo or exothermic? How did you go about doing it?
By just looking at the equation.
And then?
Or like, do you mean by just looking at the equation?
Not necessarily. Like if I want you to work out, if this is indoor exothermic, how would you do it? Not necessarily by looking at the equation, but like, like how did you do it in chapter 5 kind of thing? Well, you probably used some kind of law. Remember that law?
Hess's law?
Yeah, you probably used Hess's law to work out what the beginning enthalpy was and what the final enthalpy was with your bond enthalpies to work out the delta H. Remember that?
Yeah.
Yeah. Now, that's fine. And that's going to help us work out the delta H. Now, that's not our focus anymore. All right? We're in chapter 6. But that would help you work out the delta H, yeah? Now, we're going to be focusing on the EA, which Hess's law doesn't talk about at all, at least not at the level that you were doing it. But the thing is, see, we know that delta H is negative for our example. We know there's an activation energy, but like, tell me, assuming we were doing Hess's law to find delta H, how would you do it? Like, assuming you're back to chapter 5, and you're assuming we want you to work out the delta H of this reaction, and you had all the numbers in front of you, how would you do it?
So you find the H.
Yeah.
And then you find O.
Oxygen.
Yeah. And then you find the product.
Which is what?
OH bond times.
And then?
And then the product minus the react.
All right. And you put in the numbers and that's what you get, right? Okay, that's true. And that's all great. But I want you to think about why is the delta H this? What are we calculating? Why are we taking, 2 times the hydrogen-hydrogen bond plus the oxygen-oxygen bond and adding it together? And then why are we taking 4 times OH bond? And then, and then why subtracting it? Like what are we really trying to work out here? What does it mean?
Like the difference between
what?
The product and the reactant, the enthalpy.
Yeah, but why? Like, why is it done this way? Why is that the delta H? Apart from the fact the book told you so, like why?
Why is that the delta H? Well, because what you are finding is the delta H of the bond, right? Well, no, wait.
Well, you're finding the delta H of the reaction, which involves the bond. So really, I guess you might know, you might not know, but you haven't really verbalized it. During this reaction, when I go from the left-hand side to the right-hand side, what needs to happen? What's the mechanics of going from hydrogen gas and oxygen gas to water? What needs to occur? And I'm pretty sure you know this. You just haven't really said it.
What needs to occur from the reactant to product? Is that what you meant?
Say that again.
So like what needs to occur?
Yeah, what needs to occur?
Reactant to product.
Yeah.
You need to break bonds and then...
Yeah, exactly. You need to break the bonds. And you haven't quite said that. And I know you probably know that, but I want you to kind of say that. So you need to break the bonds. Which bonds do we need to break?
All of them.
So specifically, when you say all of them, which one are you talking about?
H.
So we need to break 2 HH bonds and a
O double bond.
O oxygen double bond. So we're going to need to break, simplistically, I mean, this is not true for all reactions, but it's pretty true for this one anyway. We're going to need to break 2 times HH bond and 1 times O O double bond, right?
Mm.
And then what happens?
And then you form bond.
Right. We're going to need to break the bond and then make the bond, right?
Yeah.
Now, break bonds need energy, right?
Mm-hmm.
And make bonds give out energy, right?
Yeah.
Now, can we make the bond without breaking the bond?
No.
Right. So why is there an activation energy?
To break the bonds.
Exactly.
Oh, okay.
So I wasn't like, you know, you've done these things before, but I'm not sure how much of it you've put together, right? So yes, you have an activation energy. So for any reaction, you have an activation energy. So for your chemical reactions, you know, you have an activation energy, which varies in size. Some are large and some are small, which remember is the energy required to, you know, make the reaction proceed. And that's what we said. But why do we need an activation energy? Well, essentially, now the amount of bonds you need to break is going to be different depending on, you know, sometimes you don't have to break everything apart, but in short, it's the energy required to break, you know, maybe not every single bond, depends on the reaction, but some of the bonds, you know, to allow the reaction to occur. If you don't break any of the bonds, the reaction can't occur because, well, a chemical reaction needs you to break some bonds.
Yeah.
Make sense?
Mm-hmm.
Right. And so how large the activation energy is for the reaction depends a bit on, you know, what reactions you're trying to break, what bonds you're trying to break, and that depends on, you know, what your reaction is. In our case here, you have to break all of them. All right. Clear on that?
Yep.
All right. Now we want to get a bit more technical. How do bonds break? How are you going to break a bond?
Activation energy.
So the activation energy plays a part, right? You'll need the activation energy. But I want to get a little bit more technical here. So basically, you will need activation energy, which means that you will need energy. You will need a certain amount of energy. But assuming you have the activation energy, what does that even mean, right? So when you break a bond, let's say you've got, simplistically, right? Let's say you've got a hydrogen-hydrogen. Now, there's different ways you could break a bond, but one way to think about it is, well, one way to think about it is as the temperature goes up, what's going to happen to the kinetic energy of the molecules?
Go up.
Right, which means they'll kind of move faster and faster, right?
Mm-hmm.
So one way to think about it is maybe the molecules will smash into each other. You know, in fact, they always smash into each other. But maybe think of it like car crashes, right? They'll smash into each other. If they're going really, really slowly, will there be a violent crash?
No.
Will the car just break up into little bits?
No.
No. Now, if you get two cars going really quickly at each other, like, you know, 200 kilometers per hour, will they break themselves up into little bits if they run into each other?
Yes.
Right. So one way to think about it is kind of like a collision, right? As the temperature goes up, well, maybe I shouldn't talk about the temperature going up just yet, because we'll get there. But just hypothetically imagine that if you have molecules, so, you know, colliding with each other, there's a chance they'll break apart, right? That could break a bond, right?
Mm.
Now, we don't know it will, but it could, depending on, you know, how fast they're traveling and all that kind of thing. So we have what are called successful collisions. Successful collisions are collisions that basically help the reaction proceed. So that's either going to break or make a bond, depending on what stage you're at. Yeah?
Mm.
So you have what are called successful collisions. Now you have to realize, even when there's no reaction, so for example, if I have hydrogen and oxygen together and with no fire, they're colliding, they're moving around all the time. So they're colliding with each other all the time.
Yes.
Right?
Mm.
But that doesn't mean, just because they're colliding with each other, does not mean they're colliding with each other in a way that gives you successful collisions to react. For a successful collision, you need to get them to react. That means they need to break the bond and maybe form the bond. Yeah?
Yeah.
Now, a successful collision depends on the success of a collision. I mean, depends on various factors, but I suppose the key factors we're going to be looking at are the energy of the collision, how energetic it is, which I guess is like, you know, how energetic the molecules are, which is kind of like, you know, how fast they're going, which, you know, ties in with temperature a bit, but we'll leave that for later when we talk about it. So basically, you want the molecules to collide successfully. If they're going to collide successfully, they need to, one, you know, do it with a lot of energy, enough to overcome their own sort of forces. And secondly, it also depends on the orientation of the collision. And now this gets a bit more complicated, and it's not very, you know, hydrogen and oxygen is not a good example because, well, they more or less, I mean, yeah, it's a decent example. It's not the best example, but think about a car, right? Think about, you know, if you've got a car crash, all right? One, you need to kind of go fast enough to crash into each other to kind of do damage, right?
Mm.
Otherwise, you know, you might go really lightly at like 1 kilometers per hour and you just touch each other and, well, no damage done, right?
Yeah.
Now, the other thing is this. Do you have any idea if you've got a car going this way and you've got a front, this is a head-on collision, right? Now, obviously, you know, if someone runs into your back of you, then that's not that bad if you're going forward, right? So that's just really an energy of the collision. But in terms of orientation, if someone runs into the side of your car versus head-on, which one do you think is worse? Or about the same?
Head-on.
You're actually wrong.
Oh.
Head-on collision, I mean, assuming the same velocity. So, you know, I'm assuming that you're, you know, going at, you know, so if this is like 100 kilometers and this is 100, and this is, let's say 100, and this is like, you know, like, well, you know, in a way you might say, you know, this is 200, right? You might say that's 200 and this is just not 200. So that's kind of true. But one thing you probably have not recognized is, where are all the safety features of the car?
The front.
Right, mostly the front, because most collisions are head-on. So therefore, there's a lot of things that are designed to basically make it safer when you crash from the front. There's a whole section that will crumple. There's the airbags. There's all that kind of thing, right?
Mm.
But if you're hitting from the side, there's not much there.
Yeah.
So actually, if you hit on the side, it's a very, very, very dangerous situation. Pretty much any high-speed crash from the side is fatal, pretty much.
Okay.
Yeah. I mean, even low-speed crashes from the side are very, very dangerous. But you can conceivably maybe, you know, moderate speed front-on crash, you can probably, if you've got a car with good safety features, you could probably survive that. High speed, well, hard to say, right? But, you know, any sort of moderate-ish, you know, thing from the side is pretty dangerous because there's no crumple zone. Your car kind of just dents in, right? So what I'm trying to demonstrate here is it depends on the speed of which you're going, and also depends on where you got hit. And that could affect the severity of the crash, right? Being hit from the front at 60 kilometers per hour is not that bad compared to being hit 60 kilometers per hour from the side. That's much worse.
Okay.
Or it's a little bit like this, right? If someone, you know, hit, you know, not the best, you know, thing, but, you know, if someone like, you know, punches you lightly-ish or kicks you lightly-ish in, let's say, I don't know, the arm or the stomach, it, well, you know, it hurts, but it's not that bad, right?
Mm.
But if they hit you in, for example, your shin or your head, that would kind of hurt, right?
Yeah.
Yeah. So, I mean, they might have kicked you with the same amount of force, but how much it hurt for you is not the same, depending on where you got hit. You see what I mean?
Yeah.
Yeah. So the same thing applies with molecules. The molecules, one is how hard they got hit. That's the energy of the collision. And the other is where they got hit and in what direction. That matters.
Mm.
Right? Now, hydrogen and oxygen, you know, I can kind of think of it as, okay, so if we hit it this way, it doesn't break that easily. If we hit it this way, it'll break more easily. Yeah?
Mm.
But another way to think about it, maybe I'll do organic chem. Maybe that's a better example. So I don't know. So for example, esterification, right? If we're taking esterification, and you've got this ethanoic acid molecule floating around, and you've got this, you know, propanol, propan-1-ol floating around. All right. So remember, for esterification, what needs to react with what? What needs to meet?
Uh,
Testing you on your, you know?
Esther?
Well, you'll get an ester, but to react to get an ester, what needs to meet?
Oh, alcohol?
Yeah? Which part of the alcohol?
OH?
Yeah, you need the OH to react with the?
Carboxylic acid?
Right. We'll just say it's a COH. We'll say it's the OH react with the COH, basically, right?
Yeah.
So imagine that these are floating around and it runs into it like, you know, this, bang. Is it going to react?
No.
Not really, right? Because it's kind of the wrong way around.
Okay.
Now, just ignore the fact that C's are the wrong way around.
Mm.
Let's say that it runs into each other like this. Is this more likely to react?
Yes.
Yeah. So that's, again, what I mean by whether the orientation matters, right? Because if it was this way around, going back, it could hit really hard and basically nothing will happen, right? So orientation matters in your molecules. And, you know, you can have all sorts of analogies. So it can be like, you know, how successful person A, like a guy, and person B, like a girl, might, you know, decide to start dating. Well, you know, that depends on, you know, how well dressed they were, like how, you know, how happy their mood, right? The energy of the interaction, how, you know, were they happy at the time they met? Were they well dressed, right? There's those sort of things, right? So that's like the energy, but it's also the orientation, right? Like, you know, how did they meet? Did they meet face to face? Or like, did they kind of like, you know, bump into each other back to back? Well, they're not really going to see each other then.
Yeah.
Which means that the success of the so-called interaction will be much lower compared to if they met face to face, kind of thing. All right, get the idea?
Yeah.
So, short version, for a reaction to occur, well, the molecule must be broken up. That's why there's an activation energy. But for an activation energy to happen, for the bond to break, that actually physically happens through, you know, collisions with other molecules, breaking them off, kind of, right? That's one common way for it to happen. But for that to happen, that means that we define that collision to be successful. But for a collision to be successful, so not only do you need to collide, you need to collide successfully. And to collide successfully, that means the energy of the collision must be high enough and the orientation of the collision must also be sort of appropriate, right? Does it make sense?
Mm-hmm.
Good. All right. And we can therefore think of the activation energy as a threshold value. It can sort of, I mean, we can go into the details about it, but basically think of the activation energy. Think of it as a threshold value, simplistically. So Paris, have you got any idea what you might want to do at uni? Or, have you thought about that?
I haven't thought about it.
All right. So is there something you do that has a threshold value? So for example, you want to get into a subject, you must get above a certain, not necessarily uni, but like, do you have to get above a certain mark to get what you want?
Sure.
All right. So let's say, you want to, hypothetically, you want to get into some subject, and you have to get above a certain mark, like 85%, right? So that's like the threshold value. And you're not the only one in the class. Lots of people in the class, want to get that, to get into that program. Well, your Maxwell-Boltzmann distribution comes in. You've got people with different sort of marks. And this is your cutoff. This is like a minimum mark required to get into that program, which is analogous to your activation energy. So if you get a good enough mark, you're in this group. You're the in group. You can react. You can get into that program. But if you're over here, not enough energy to react. Does that make sense?
Mm.
Clear on that?
Yeah.
All right. So that means we basically want any particles with sufficient energy. So you want a blue to meet, so you want a particle with a blue to basically interact with another blue particle because they'll have sufficient energy to meet and react. And then hopefully orientation will happen and then they will react and you're done, right?
Yeah.
All right. So now that you understand how a reaction proceeds, let's now think about factors that affect a reaction rate. Do you know what factors affect reaction rate? You may have done this in science earlier as well. What factors affect the rate of reaction?
What's the rate of reaction?
How quickly a reaction proceeds.
I feel like I have done it.
You probably have. We're going into it in a bit more detail, obviously. We're going to be talking about why they affect it. But do you remember what the factors are?
No.
Okay. So one of them is temperature. Does that ring a bell?
Yeah.
All right. Another one is concentration.
Mm-hmm.
Another one is particle size. Now, do you remember what a catalyst is?
Mm-hmm.
What's a catalyst?
Just something that speed up the reaction.
So would it affect reaction rate?
Yes.
Right. Now, there's also, pressure, for example. And there's also other things that haven't written in your book, but, we'll stick with these for the moment, but basically, more generally, I think it's surface area. And you can kind of think of like sort of agitation or mixing. Right. So here's the thing, right? If you want things to react quickly, what do you need for that to happen? Like, think sort of based on what we said about reactions. If you want things to react quickly, what would you need?
If you want, sorry, can you say again?
If you want your reactants to react in a quick manner, what would you need? What kind of determines your reaction rate?
Do you need more energy?
Well, you do, and that will help. But I guess I'm asking at a more sort of fundamental level. And then we're trying to see how factors could help along with that. So you want your hydrogen to react with oxygen, for example, or you want your ethanoic acid to react with propanol, and you want lots of them. Like you want it to react quickly. So remember, you don't just have one and one, you've got lots of them, right?
Yeah.
How do you measure rate? Like what determines quick or slow? How do you measure if the rate of reaction is quick or is it slow in terms of, you know?
Like how much you get in an amount of time?
Right, it's basically how many reacted in an amount of time, right? And if you're going to get a certain amount to react in an amount of time, what does that, like, given how reactions occur, how do you, like, what would need to happen to make sure you get more reactions in the 1 unit time or 1 unit of time? How to get more reactions occur, you know, at the same time, I suppose?
You have more reactants? Okay, maybe not.
Maybe yes, maybe no. Like what fundamentally needs to happen? What about your collisions?
Do you need to have more successful collisions?
Exactly. So basically, we basically need, so reaction rate is essentially determined by the number of successful collisions per second. Right? The more successful collisions you've got per second, the faster your reaction rate. Make sense?
Yep.
All right. Let's think about this. How could you increase the number of successful collisions of your reactant? Just think of your reactants as cars, right? How could you get them to successfully collide with each other? What sort of concepts would you think of? Like if you imagine you're allowed to change certain aspects, right? How to increase the number or the rate of successful collisions?
Can you increase the energy?
Well, you would, but when you say increase the energy, what do you mean? As in, like, that is the right answer, but I guess I want you to you to understand it more fundamentally. Like, so imagine you've got cars, you know, running around.
Yeah.
And a successful collision in this case is defined as a car crash that causes damage. You know, how would you increase that successful collision rate kind of thing?
To go faster.
Right. All right. Sure. So analogy, you know, cars on road. To increase collision rate, one option is the cars go faster. Any other thing that you could do, perhaps? So yes, you can make the cars go faster. Anything else?
Change the orientation.
Yes, that's probably not the, you know, hard to. So I know what you're getting at. That is true. There is the change the orientation. So I guess, you know, make sure that lots of cars are likely to T-bone each other as opposed to front-end collision. Yeah. In fact, you know, yeah, change the orientation of collision. So influence how the collision orientation occurs. So maybe change. So yeah. Any other ways? It's hard to kind of do that with the car analogy, but yes, you could. If you could somehow do it, then yes.
Or if you have more.
Yeah, right? Now, I know your idea and it's on the right track. Is it really a question of more cars?
I think more concentrated.
Yeah, exactly. More cars per area. Exactly. So basically, they're more crowded, right? And yes, you're right. That in terms of analogy is direct to concentration as far as chemistry goes. So basically, like, you know, if you have a really big country like Australia, you could have potentially you could have more cars than a country like, you know, Singapore, but you're more likely to run into a car, you know, like if you spread cars evenly throughout Australia and you spread cars evenly throughout Singapore, well, Singapore might have less cars, but you're more likely to run into another car. You know what I mean?
Mm.
All right. Anything else you can think of? So you can make the cars run faster. Yes. You could have more cars per area. Yes. You can change the orientation of collision. Yes.
Mm.
They're probably as far as the car analogy goes, that's probably most likely. Yeah.
Mm-hmm.
All right. So let's use another analogy. Let's now assume that we've got students trying to get into a course. All right. How could you increase the rate of students getting into the course?
You have more master students.
Yep. So one is increase the caliber of the applicants. So they're, you know, better, basically. Any other way?
Mm. You can just have more students in general.
Right. You could just have more, you know, students. Now, the more students doesn't really, you know, increase the rate, right? It just increases the number. How do you increase the rate?
More students in the class.
Right, taking the exam at the same time. So in other words, you know, maybe before, you know, 100 people were taking the exam a year. Now I'm getting 1,000 people taking the exam a year, right?
Mm.
Anything else you could do to increase the rate of getting into the course?
Mm.
Any ideas?
No.
What if we dropped the entrance mark?
Oh, that's true.
So we basically made the test easier or drop the threshold, right? So drop the threshold. Or alternatively, make test easier. Right? So all of these things, more or less, are analogous to how you could get molecule to react more likely to be successful in reacting. So just like getting a student to be more likely to be successful in getting to the course, or getting cars more likely to be successful to crash into each other, these are all sort of analogies to try to kind of get at how molecules could potentially more successfully collide with each other and therefore react. Does that make sense?
Mm.
Now, we will be going into the details of this, and I want you to think of why, for homework, I want you to think about for each one I've listed here, why, you know, they affect reaction rate and how, in detail, and we will need to go into that. But before we do, let's just identify the general trend. If we increase the temperature, do you know what will happen to reaction rate?
Also,
Right. If we increase concentration, what will happen to reaction rate? Yep. And if we increase pressure, reaction rate will go up. If we increase particle size,
oh,
not sure. Any ideas?
Go down.
Yeah, you would actually go down. You understand why?
I don't know. I just feel like if it's bigger, it's harder to break.
That's not the reason. You got the wrong reason.
Okay.
You got the wrong reason. Think of particles. Particle size is really only relevant for solids. So really, that's why I don't really think particle size. I mean, particle size is true, but I think you should probably think not so much about particle size, but think of it as surface area. So for example, I mean, I don't know if you've gone camping before, but do you think a log burns faster or a twig burns faster?
A what? Sorry, what?
Like if you're burning wood, do you think a big thick log burns faster or twigs?
Twigs.
Right, you could probably put lots and lots and lots and lots of twigs in, more twigs than the total volume of the log, but it will still burn through the twigs faster than it'll burn through the log, right?
Mm-hmm.
Why is that?
Because twigs are smaller in size.
But even if I have huge number of twigs so that it ends up being the same size as a log, why can I burn through more volumes of twigs faster than I burn through one log? So I'm not comparing one twig and one log. I'm comparing a huge number of twigs and one log.
Oh, but you're still burning like the same.
Yeah, so if I burn the same amount of wood, but one is like lots and lots of twigs and one is a log, the twigs will still burn faster, a lot faster. You're not sure why?
I don't know. Yeah. Okay. Yeah. No.
Okay. Well, I want you to think about it this week. I'll give you a hint. It's kind of like, 5, and it's to do with solids. Now, catalyst. If we have a catalyst, what happens to the reaction rate?
Goes up.
Correct? If we increase the surface area, what happens to the reaction rate? Any ideas?
Goes down.
Actually, it goes up.
But when we are talking about particle size, are we talking about surface area or something else?
Yeah, so you have it the wrong way around. The smaller the particle size, the bigger the surface area. Total surface area. Have a think about it.
Okay.
All right. What about agitation or mixing?
Goes up.
Yeah. Now, these things are important, but before we go through each and every one in detail, which we will need to do, and some of them you kind of get, some of them you don't get as much. Now, I get the idea that you sort of understand concentration, right? You might not yet fully understand temperature, although you know part of it, but not necessarily the most important part. We will need to go through that. You maybe like try to think of the analogies we had, try to think of what these things are, all right? And try to, as much as you can, come up with, explanations for why these factors, when affected in the ways we've talked about. So why does temperature go up, reaction rate goes up? Why does when concentration goes up, reaction rate goes up? I think you pretty much get the second one. Why is it when particle size goes up, reaction rate goes down? I said hint, talk about surface area. Think about surface area. Why is it when surface area goes up, for solids, reaction rate goes up? Think about what a catalyst is, if you remember, the mechanics of a catalyst. Why is it when we have a catalyst, how does that affect our reaction rate? Why does that make our reaction rate go up? When we mix something, why does that make our reaction rate goes up? These are the correct answers. But I do want, and we do need to, go into why each and every one of these things end up making the reaction rate go up or down at a detailed level, right?
Okay.
Now, we won't have time to do that today, so we'll do that next week. But to kind of help next week's lesson along, as I said, I want you to think about it before. Think of the sort of explanations you can come up with. I'll ask you what you think about it, and then, and we'll try and work off that. And then to get you towards what, is a good way to think about why each factor listed will affect the reaction rate in the way we have said.
Okay.